Hello and welcome again to our study of limits. Last time we looked at the informal definition of limits and calculated some limits using an analytic approach, a graphical approach, and a numerical approach. We also saw some examples of functions where they didn't have a limit at a certain point, some poorly behaved functions. This lecture will take the idea of limit and use it to define a concept called continuity. A function informally is continuous if it doesn't have any breaks or holes in it. As usual, I'd like to talk about continuity to begin the discussion with a series of examples. Let's look at the function f of x equals 1 over x. Here's a picture of that function. And you can see that it looks continuous everywhere. There aren't any problems except at the origin. And at the origin, it looks like the function is poorly behaved. In fact, even worse, it's not even defined at the origin, is it? So this function will not be continuous at x equals 0 because it's not even defined there. And worse off, you can't repair it. You can't define the function to be something at 0 to make it continuous. In a sense, you can't pull those two pieces and glue them together without damaging the other parts of the function. On the other hand, here's a function that also has a discontinuity, but it can be repaired. Remember our old friend x squared minus 4 over x minus 2? Well, that function, if you simplify it, cancel the common term x minus 2, is the same as the function x plus 2, except if x equals 2. So what's the graph of g of x, the original function? Well, it's the same as the graph of x plus 2, except there's a hole when x is equal to 2. Here's a picture of the graph of x squared minus 4 over x minus 2, a line with a hole in it. It's not continuous at 2, is it? It's not even defined there. But it can be saved. We could define the function at 2 to make it a fully continuous line. What does the function want to be at 2? Well, it wants to be equal to its limit, which is 4. So if you define this function to be 4 when x is 2, you would then have a continuous function. Kind of neat. We could remove the discontinuity. Let's look at another function defined by two rules. The first rule for x less than or equal to 0 is x plus 2, a straight line. And for x bigger than 0, it's a parabola x squared plus 2. Here's a picture of that function. Is that function continuous everywhere? Well, it's clearly continuous to the left of the origin, because that's the straight line. It's clearly continuous to the right, because that's the parabola. The only problem is what happens when x is 0? Well, thank goodness it's glued together correctly. The two pieces of the function agree when x is 0, so that function is continuous for all x. Now, that said, imagine for a moment I change the second rule to say be x squared plus 1. That would lower the parabola 1 unit, wouldn't it? And now it would not be continuous at x equals 0. It would be defined there, but the left-hand limit would want to be 2 as I approach from the left, but the right-hand limit as I approach from the right would now be 1, and those two limits would not agree. So, we've seen, I think now, the idea of continuity. Let's look at one of our old favorites from last time, the so-called hiccup function, and talk about its continuity. Here's a graph of the hiccup function. It's defined to be as follows. When x is equal to 2, the function's defined to be 3. And for all other x values, the function is equal to 1. In other words, it motors along at 1, 1, 1, 1, 1, and then it hiccups to 3, and then it goes back to 1. So, is this function continuous for all real values of x? Well, it is except for x equals 2. That's the bad point. And at 2, it's not continuous because it's broken there. It's as if somebody was really stupid and defined the function at 2 to be 3. What does it want to be when x is 2? Of course it wants to be 1. So this is a removable discontinuity. We can change the function by defining the value at 2, a single point, change that definition, and we turn it into a continuous function. It's basically fill in the dot, and you make it into a continuous function. Okay, we've seen a lot of examples now of some continuity issues. What's the definition of continuity? Here it is. It's a 3-part definition. We say that a function is continuous at a point C if the following 3 conditions hold. First of all, you better be defined there. The function has to exist at that point. Second of all, its limit has to exist at that point. And third of all, the limit has to equal the value at that point. For instance, in that previous example we saw, the hiccup function, the function was defined there, wasn't it? It was defined at 2. It also had a limit as I approached 2, but they didn't agree. It hiccuped up to 3. It didn't respect its limit. I like to say it that way. The value of the function did not respect the limit as I approached. If you recall back the function 1 over x, the first example I did today, that violates the first part of this definition because at 0, the function was not even defined. You have no hope of being continuous at a point that doesn't even exist in the domain. Okay, so that's the 3-pronged definition of continuity. Let's look at a case where we have a function defined on a closed interval, where we have to look a little closer at what happens at the endpoints of that interval. I'd like to look at the following example. It's a semicircle. It's the square root of 4 minus x squared. Here's a picture of that semicircle. And notice that its domain is the interval minus 2 to 2, including the endpoints. Now, if you notice on this picture, it's clearly continuous for the open interval minus 2 to 2. The only issue is, what do we do about the endpoints? Because you can't really take a limit approaching 2 because the function's not even defined for values greater than 2. So what we do are so-called one-sided limits, and I've talked about that a little bit previously. Let's look at what happens to this function as I approach 2 from the left and I approach minus 2 from the right. As I approach 2 from the left, the function gets towards 0. And as I approach minus 2 from the right, the function also tends to 0. Notice this fairly confusing notation. I'll look at the second term, limit as x approaches minus 2, and then there's a little plus sign above the 2. That means you approach from values greater than minus 2. Graphically speaking, you approach minus 2 from values like minus 1, minus 1.5, getting closer and closer to minus 2, but only from the right. Why? Because you can't approach from the other direction, can you? It's not even defined. So what we say is, in this case, that the function here, this semicircle, is continuous on the closed interval minus 2 to 2. Why? Because the limits at the endpoints, the one-sided limits, respect the function values there. Okay. Let's look at a function that comes up a lot in applications in real life. This is the so-called greatest integer function. Here's how it's defined. The greatest integer of a number x is equal to the greatest integer n less than or equal to x. Now that's kind of confusing. Let me do some examples. The greatest integer of 2.5 is 2, because 2 is the biggest integer less than or equal to 2.5. How about the greatest integer of 0? Well, that would just be 0 because 0 is already an integer. How about minus 2.5? Well, the greatest integer would be minus 3 because you have to go below minus 2.5. Now, what happens here with the limits of this function as, say, we approach 0 from both sides? As I approach 0 from the left, the greatest integer of x will be minus 1. But as I approach 0 from the right, the greatest integer will be 0. And we see this would be true for any integer value. So this function is not continuous at integer values. It does have one-sided limits there. Here's a picture of the greatest integer function. And notice, let's look, say, when x is 1 on this picture. When x is 1, if I approach from the left, the greatest integer is 0, isn't it? It's going along 0, 0, 0, 0, 0. And then it hops up. And when x is 1, the function value is 1. And when x is 1.5, say, it's also 1. It has these discontinuities at every integer value. Here's an application of the greatest integer function. It's kind of a complicated application. You can sort of see how applied math can be sometimes pretty rough going. I looked up my cell phone bill the other day, and here's what they charge me. My service charges me $39.99 for the first 450 minutes. And then if I go over, it charges me 45 cents for each additional minute or fraction thereof. Okay, I'm not sure if that's your cell plan, but that's what mine is currently. Maybe it's too expensive, I don't know. Let's model this plan with the greatest integer function, and we'll talk about the nature of the model. Let's make sure we understand how this works. If I talk for 450 minutes in a month, they charge me $39.99. But suppose I go over by 1/10 of a minute, say 450.1. Well, they're going to stick me with an extra 45 cents, aren't they, for that extra part of a minute. And my charge would be 40.44, which is 39.99, plus that extra minute, which is 45 cents. Keep that number in mind, 40.44. Well, here's a model of that cell phone plan. It's a complicated model, and there are other ways of writing this model, but here's one way of writing it. You can see how difficult applied math can be, but here's a model you could feed into your computer if you work for that cell phone company, and then you would roll out all the charges. It's 39.99 for usage up to 450 minutes. I'm using T to signify the number of minutes. And then it's 39.99 minus 0.45 times the greatest integer of the quantity 450 minus t. Whoa, that's kind of complicated, isn't it? And that's the model for t bigger than 450. Let's check the model on a couple of values. Suppose I talk for 450 minutes. Well, then I would use the first rule, wouldn't I? And I would just be charged 39.99. But how about that case where I used an extra 1/10 of a minute? Let's use the model to calculate C, the cost of 450.1. Well, watch how the model works. It's kind of neat. It's 39.99 minus 0.45 times the greatest integer of 450 minus 450.1 minus t. Well, let's simplify that. 450 minus 450.1 is minus 0.1. And the greatest integer in minus 0.1 is minus 1. So our equation now is 39.99 minus 0.45 times the quantity minus 1. The minus signs cancel each other, and bingo, we have the final answer, 39.99 plus 0.45, which is 40.44. Do you remember that number from the last slide? Yeah, that was the correct answer. Good. Notice that this function for the cell phone plan is not continuous at each integer greater than or equal to 450. It's because they jump every time you use another minute. Again, complicated model, I admit it. We would not expect, I think, in our calculus courses for students to come up with this model, but we would expect them to be able to use it if it were given to them. Let's talk about some properties of continuity. These are sort of based on the same properties of limits. For instance, if you have a couple of continuous functions at a point C, then their sum, their difference, their product, their quotient will all be continuous at C, except in the rare case that you're dividing by 0. And even the composition of continuous functions is continuous. Remember what composition is. If I have the function, say, x squared plus 4, that's one function, and then I take the square root of it, I've composed it with the square root function, and that's also continuous then. So the composition of continuous functions is also going to be continuous. And in general, all the functions we've learned to love in mathematics, the polynomials, the trigonometric functions, and even later, the logarithmic functions, the exponential function. All these functions are going to turn out to be continuous on their domains. Be careful, on their domains. That'll come up in a moment. So nice functions are continuous everywhere on their domains. Here's an example of that. Let's look at the tangent function. Let's discuss the continuity of our friend tan x. Well, let me remind you what the graph looks like, and then we'll come back and talk about it. Here's the graph of the tangent function. Not only is this is one of the functions I carry around with me in my back pocket, I also carry around its graph. Trust me, we'll be looking at the tangent function over and over again in this course. So please sort of remember what this graph looks like. What's interesting about this graph is it's not defined at pi over 2, 3 pi over 2, and minus pi over 2, etc. It has a lot of points where the function is not even defined. The reason for that is, of course, that the tangent is sine over cosine, and cosine of pi over 2 or 3 pi over 2, etc., is 0, and you can't divide by 0 in mathematics. So this function is not continuous at pi over 2, 3 pi over 2, 5 pi over 2, etc., and then all the negative values too, minus 3 pi over 2, minus 5 pi over 2, etc. Well, why isn't it continuous there? Well, it's not even defined there. It doesn't even exist at those points. You have no hope of being continuous if you aren't defined. Now, can we save this function? Can we define it at, say, pi over 2 to turn it into a continuous function? And I hope you realize the answer is no, because on one hand, the left-hand limit as I approach pi over 2 is going off to plus infinity, isn't it? But on the right-hand side, it's going down to minus infinity, and there's no single value L that I could define so that it would glue those pieces together and make it continuous. So that's kind of sad. You can't save that function and turn it into a continuous function. Well, now let's look at one that you can do it. How about our old friend sine x over x? Sine x over x. Remember, we looked at this function last time, and the limit as x approached 0 was equal to 1. In other words, when x is near 0, sine x and x are about the same. And they actually have a limit, that limit of that quotient equals 1. Now, let's step back. Is the function continuous at 0? Answer, no. It's not even defined there. Can I make it continuous at 0? Can I define it at 0 to turn this function into a continuous function for all real values of x? And the answer is yes. All I have to do is say, what does it want to be when x gets closer and closer to 0? What's the limit at 0? Oh, it wants to be 1. Remember the graph of this function. Here's a picture of it. When we graphed this function, there was a hole at the point 0, 1, because it wasn't defined there, but it wanted to be. The limit was 1. Well, now I can define a new function equal to sine x over x for x not 0, and equal to 1 for x equal to 0. And lo and behold, we now have a function that's continuous for all real values of x. We call this point x equals 0 a removable discontinuity. I could remove it by defining the function to equal its limit at that point. Now remember this function. This was that wild function sine 1 over x that went up and down, and as I got closer and closer to 0, it went crazy. Well, can we save this function? Can we turn it into a continuous function at the origin? Well, you might remember that it never settled down. It kept going between -1 and 1. So even if I tried to define it, say, to be 0 when x was 0, that function is not going to be continuous at 0. The limit does not exist as x approaches 0. Even though it's defined there, big deal. It doesn't respect its limit. Well, it can't respect its limit. It doesn't have a limit as x approaches 0. That violates the second part of the definition of limit. And this is a non-removable discontinuity at 0. You can't define it to be a single number L and turn it into a continuous function. Here's a graph of that function again. I think I encouraged you last time to graph this on your graphing calculator and zoom in near 0, and you'll see that crazy behavior. Well, let's take that function, the crazy behavior function, and modify it slightly. This is pretty cool. I think you'll get a great picture here with your graphing utility. Let's now look at a function related to the crazy one, except I'm going to put an x in the front. It's now x times sine 1 over x if x is not 0. And then I'm going to define it to be 0 if x equals 0. So we have a new function. But now things are a little bit different because I've got that x in the front. So as I approach 0, the x values, that x in the front is going to approach 0, isn't it? And sine, of course that sine 1 over x is going up and down, but it's always bounded between -1 and 1. So I'm kind of getting the function squeezed down towards 0. In fact, algebraically, you can see that x sine 1 over x is always going to be less than or equal to the absolute value of x and greater than or equal to minus absolute value of x. Here's a graph of that function. I've graphed this x sine 1 over x, which is going up and down, but it's being what we call in mathematics and engineering, it's being damped. It's a motion that is getting, the motion is getting smaller and smaller. It's being damped. And in fact, it's below the absolute value function. That's that v that we've talked about, the absolute value function, and it's above the negative absolute value function. So this function is really cool looking, isn't it? It's motoring up and down, but it's getting smaller and smaller, the up and down nature of it. And in fact, as a limit, it tends to 0. So this function is actually continuous for all values of x. And if you look again in some calculus books, you'll see that they prove that using something called the squeeze theorem. The squeeze theorem basically says the graph of this crazy function is being squeezed in between the absolute value function and the minus absolute value function. And both of those functions go to 0, don't they? So the one in between must go to 0 as well. Great. We now, I think, have a good feel for continuity. Let me show you one of the major applications of continuity in applied mathematics, and it's based on a fairly important theorem called the intermediate value theorem. Here's how the theorem works. If you have a continuous function on a closed interval, and you pick a value in between f of a and f of b, so those better not be equal to each other, and you pick that value, let's call it k, then there's some number between a and b such that f of c equals k. Let me show you a picture of that. A picture is much easier to understand than the words. Here we've got a continuous function on the interval ab, and f of a and f of b are not equal to each other. So I pick a value k in between f of a and f of b. The theorem says that there's some number c in between a and b such that f of c equals k. In other words, you take a horizontal line from k, it will have to bump into the curve because the curve is continuous. There's no breaks in it. And then you go down to c. This is an existence theorem. It doesn't tell you how to find C, but it says it exists. And in fact, there may be more than one value of C. And in this case, in this picture, you see that there would be at least maybe two more values where f of C equals K. Here's an application of that theorem. Something that you do all the time with your graphing calculator, and that's finding roots to equations. Let's look at the polynomial x cubed plus 2x minus 1. I claim it has a zero, it has a root on the interval 0, 1. Let's see how the theorem shows that. Well, first evaluate the function at 0, and f of 0 is minus 1. That's negative. How about evaluating it at 1? Well, f of 1 is 2, and that's positive. So we have f of 0 and f of 1. They are not equal to each other. That means for every value in between minus 1 and 2, there must be a C value that goes to it. In particular, pick 0. Here's the picture. F of 0 is minus 1. F of 1 was 2. That means the function, the graph, has to cross the x-axis. I'm letting my k value be 0 here, and hence there must be some C, which is the root. Kind of neat how it works. Now, the function has to be continuous, so you have to realize, oh, polynomials are continuous on their domains, so they're continuous everywhere. So, what is the root? How would you find the root? Well, it's in between 0 and 1. I don't know what it is. Here, let me give you some ideas on how you find the root. You could then bisect the interval. Say, look at 1/2. What's f of 1/2? Well, if you plug that in, you get an 1/8. So that's positive. So now we have f of 0 is minus 1, and f of 1/2 is an 1/8. So it went from negative to positive. The root must be in between 0 and 1/2. Good. And you could bisect again and again and again. There are faster methods than bisection. One is called Newton's method. It's not on the AP examination, but it's in every mathematics text, and it's a very nice technique for finding roots to equations. Or, of course, you could use your graphing utility. They all have built-in root finders, and if you do that, you get an approximation of 0.4534. At least that's what I got on my calculator. I invite you to do it on your calculator. But note that the root is indeed between 0 and 1/2. Let's look at a problem that sometimes appears on advanced placement examinations, or this style of problem. What they do is they give you a function defined by two rules, and then it has an unknown constant, and they want you to find that constant. So here's an example. The function is 3x squared if x is greater than or equal to 1. That's a parabola. And it's a times x minus 4 if x is less than 1. So basically, this function has two pieces, and I want to glue those pieces together so that it's continuous at 1. That's the only problem child here, what happens at 1. Everything else is in good shape. So what should a be in order to make this a continuous function? Well, what you want to do is you want the limits from both sides to be the same, don't you? So here's our function. Analyzing it near 1, you get the following, that when x is bigger than 1, it wants to be 3x squared, so at 1 it's 3. Good. When I'm less than 1, it wants to be ax minus 4, but I want when x is 1 to be a times 1 minus 4. So a minus 4 has to be 3. That implies that a is 7. So if you put 7 for a, the second rule becomes 7x minus 4, and now you have a function that's continuous. I invite you to graph that in your leisure. Now, next time we're going to look at functions that behave really in funny ways near when x goes off to the left or the right to infinity, or perhaps when we go near a point where the function is not even defined. Let me show you an example of such a function. This is the graph of x minus 1 over x minus 2. Next time we'll talk about the following questions. What happens to this function as I get closer and closer to 2? I think you see that as I get close to 2 from the right, the function goes off to plus infinity, gets larger and larger. And as I approach from the left, it goes down to minus infinity. And then we'll also ask, what happens as I go out to large positive values of x or large negative values of x? And again, I think you see that something interesting is happening. And we'll talk about those asymptotes next time. Thanks very much, and see you next time.